This is Jimmy. I'm from RIS 2020 Cohort. My research topic this summer is the optimization-based controller for legged robots through direct collocation approach. Currently, we have multiple leg systems used in the research, and we can group them by the number of the legs they have. Example for the bipedal robot like the HRP2, quadrupedal robots like Animal, and hexapod like Mat6, which is also the testbed for our research. We all know that we can handcraft the motion for the robot, but it's obviously tedious. So question arises, how to automatically generate motion forces given a high-level task? And this is the field of optimal control. There are two methods to formulate the problem, namely trajectory optimization and dynamics programming. Under each method, we have several sub-methods, but here we're going to use direct collocation in the following slides. But actually, we also have attempted other methods like sequential linear quadratic programming. The way we discretize and interpolate the nodes by cubic Hermite methods is a way to connect the nodes and form a curve with consideration of tangential at each node. This is the overall architecture. You can see a pipeline which consists of the main flow colored in blue and accelerate blocks colored in crimson. A goalpost on the elevation map is firstly specified, and then the planner generates an intermediate post towards user-specified goal. Robot solves an optimization problem online to select a set of footholds on the terrain map. The initial state and final state then transfer to the boundary condition for direct collocation optimizer, which solves minimum energy trajectory for body and effector. Low-level controller then converts whole body motion trajectory into joint angle trajectory and torque trajectory to control motors. In the red box is the main problem we're going to solve, and we can divide into two parts: foothold selection and whole body motion planner. Foothold selection can also be understood as the optimal stance. So we can think the problem as to minimize a cost to go function with the constraints. And for the constraint, we have equality and inequality two types. Equality constraints like the dynamics model we need to satisfy, and inequality constraint like the friction coil that the forces exerted on the feet need to fall into. Another issue is how to transform a discrete gait pattern to a continuous decision variable. On the graph at the right-hand side is an example of foot force and position profiles. Blue lines are force or position spline curves. Red circles are locations of spline intermediate nodes. Black dashed line indicate the lag mode transition time instance. Force profile has 6 intermediate nodes. Position profile has 2 intermediate nodes in this case, but actually we can adjust the number of nodes based on our need. Here are 2 examples of our real robot testing. We can see that A can climb stairs as well as the slope with steep incline. So overall, there are 2 novelties in our research. Terrain planning. A robot could capture the elevation mapping around a large distance to the robot. Motion planning could be applied in a high-level task. Another one is the capability of shifting the head with relatively small locomotion in XY plane. And it might be one of the best performance of its kind, and climbing especially. And we can see the climbing skill of Mat6 outperform Boston Dynamics bar. Finally, I want to express my gratitude towards RIS 2020 Cohort, Ms. Rachel Bertha, and Dr. John Dolan. Thank you.